Okay. Hi, everybody. This is the Physics of Bitcoin show. Um, let me- do you see a split screen or do you see
Yeah, I see three sections. It's a
three
three split.
sections? It's a new thing. It's a different. Let me see if I can find a better setup. Maybe still. Anyway, I don't know why we have. Let me see if I can get rid of this. Remove. Oh, yeah. Okay. Good. Let me try this. All right, so it's the Physics of Bitcoin show. This is number 18. It's 423. So the Physics of Bitcoin show is about talking about Bitcoin, but with a different angle. We look at more, from a evidence-based way, the Bitcoin behavior. We have this particular point of view where we found these long-term trends with this the power law. There is a precise relationship between price and time, but also other things like addresses and hash rate. And so, both of us have a PhD in physics, and we have spent our career analyzing data in many different contexts. And so, in different way, different paths, we arrived to Bitcoin and kind of almost independently found the Bitcoin power law, or we work on it, verified it, and this is what we are interested in is in understanding Bitcoin. Taking this more scientific point of view. So every week we go deeper and we look at a particular angle, explore a particular topic, and this is the nature of the show. If you never tuned before, Stephen.
Yeah, nothing to add to that. Thank you for joining us, and I will actually jump back into the slides.
Yep.
And I'm going to talk about, does supply influence Bitcoin? Does liquidity influence Bitcoin? And really the difference between what you see in the bubbles and in the Power Law core.
Very good.
So number 18, April 23rd. And the question I pose is, do supply and liquidity matter for the core? You can almost tell from the question what the answer might be. Okay, so first I want to show you this very interesting graph of everything that came from a couple of astrophysicists based in Australia at the Australian National University. It's quite interesting, but it shows how pervasive power laws are in physics and in the university, and power law relationships, as well as just the strict, what we call laws of physics, of which there are 4 fundamental plus a 5th mechanism that we call Higgs, all of which have power law components. Then I'm going to ask, does supply matter? And then how much and when does liquidity matter? So what I've done is multiple linear regressions that include supply and liquidity terms, and then we'll see what the weights turn out to be with those. And what we find really is it's only due to the bubble regions that they get significant weights. In the power law core, the weights for both of these drop to very close to 0. So this is what I call the graph of everything. I don't think they use that name, but that's what it looks like to me, because everything we know of in reality and in physics and in really theoretical physics to some extent is on this graph. And it's roughly a googol by a googol squared. What do I mean by that? A googol is 10 raised to the 100 power, one with 100 zeros after it. And we've got a dynamic range on the y-axis that extends more than 100 orders of magnitude. And it has mass. And there are actually multiple axes. There's the mass in grams, there's the mass in solar mass units. And on the right-hand side, you see the mass in what we like to use in physics, GeV, giga electron volts. 1 giga electron volt, by the way, is about equal to the rest mass of a proton. So you've got mass on the y-axis, and then you've got physical radius On the x-axis, it's shown at the bottom and at the top. And at the bottom, we use the familiar centimeters. And at the top, we use what astronomers like to use, which is megaparsecs. But you can see by looking at the numbers that they go, if you look at grams, which is the innermost y-axis on the left, it goes from, minus 50 something up to over 60. So that's 110 orders of magnitude, well over Google. And on the x-axis, it goes from minus 40 centimeters, which is below the Planck length at 10 to the minus 33 centimeters, and it goes up to, 55. So that's already 95 orders of magnitude, very close to a Google as well. Now, on the graph itself, a lot of things are represented, and you'll see some power laws. One in particular is the power law for black holes. So if you start from the middle left, you'll see this black triangle QG. That refers to quantum gravity. And then there's a straight line with a label black holes, and it goes up and to the right. It's got a slope of 1, basically, because black holes have a radius that is absolutely proportional to their mass. That's the definition, but it's balancing, basically it's balancing the gravitational potential against the speed of light squared. And so that gives you that straight line, which is unusual with respect to matter. The more common matter you can see in this pink domain, and it's got everything from, the sun and the earth and planets in the upper portion of the pink region. Then you see that purplish band, you go up there and you get the large scale structure with globular clusters and galaxy clusters, all the way up to the universe at large, which is this Hubble radius. So those things you see also follow a band or a line, and that is a slope of 3 as a power law. Basically, it's saying that the mass goes as some sort of density domain that's roughly constant along these bands, and then it goes as the cube of the scale. For example, if we jump back to the one in the pink region that has atoms and COVID virus and bacteria, humans, whales, and goes all the way up to the sun, that's roughly the density of water. As you know, humans have the density of water.
Yep.
Well, the sun is on there too. Well, actually, the sun's density is equal to water. It's 1.4 grams per cc, which is just 40% greater than the density of water. So that's a, mass going as the size to the cube, all the way up over many, many orders of magnitude.
So that, just to explain, because some people will be confused, right? Because it's not the sun made of hydrogen and helium, right? So it's the average, because inside the sun, the density is crazy. It's incredible densities we have inside the sun, but outside it will be plasma that is even less dense than a gas here on Earth. And so if you take an average, you get actually something close to water, because physicists like approximations like that, right? Like, who cares if a factor of 2, 3, 4, it's all
not even
in the same,
factor of 1.4, right?
It's in the same order of magnitude, right? So basically water, And also what is cool in this graph is that human, it's at the center, right? It's a center of everything. But it's interesting. It's interesting that we are like the measure of a universe, right? The measure of everything.
Yes.
It's really cool.
We've gone down with our particle physics down to, that lower brown looking triangle where it says the Compton limit, and it's got some of the key fundamental particles laid out there, and they follow an inverse, because the fundamental wavelength associated with them, which is the Compton wavelength, is 1 over their energy, 1 over their rest mass energy, right? So that's what you're seeing, that line, which is perpendicular to the black hole line, right? So we've got quantum there, we've got gravity in the upper left, defined by black holes, and they intersect where you would have quantum gravity, which is, as we know, an unsolved problem. So there's really a lot going on here. That purple band it shows domination, purple. It shows this omega with a sub M, that's matter, the domain of matter. And then to the right, it's showing the domain of dark energy, basically.
Yeah.
But I just wanted to show this because it shows how ubiquitous power laws are.
The universe is all about scaling laws. It's all about, and if you understand scaling laws, you understand the universe. That is so important. And power laws are all about scaling law, how things scale up as they grow. It's really a critical. I love this graph. It's amazing. I never saw it. I never saw it.
I never saw it until last week, and I said,
Wow.
"Oh, I've got to show this."
It's beautiful.
And I just sorted out where it came from, which is Lynn Weaver, who I've heard of, and his associate at Australian National University in Canberra, who used to be a big supercomputer customer of mine as well, and the Planetary Science Institute down there.
Yeah. I recently I'm in this. I'm listening a lot about this ancient civilization stuff, and we talk about all of these numerology things. These numbers that determine the nature of a universe, and it's all garbage. Because there is nothing to it, and then there is real stuff, real math that really is the secret of the universe. And I wish people spent more time studying these things instead of the pyramids telling us the secret of the universe. It's so ridiculous.
Yeah, there's so much here in reality to study.
Exactly.
So we apply those methods to to Bitcoin analysis. And here's another analogy that comes from astrophysics, and it's the stellar nucleosynthesis analogy. Actually, the density at the sun's core is only 2 orders of magnitude higher. It's 150 grams per cc in the core, but you get a square term, so that helps. But really, you've got very high temperatures as well because of the overlaying pressures, and that's how you get nucleosynthesis, where the sun is converting protons into alpha nuclei, or, the nucleus of the hydrogen into the nucleus of helium. And that's what powers the sun. And that rate goes as the square of the density and 2 exponential terms. And the first one is a temperature term. So the higher the temperature is, the more high energy protons you have. You're trying to smash them together, but they resist each other because they're repulsive, right? They both have positive electric charges. So you've got to overcome what's called the Coulomb barrier there. And there's this other term, a second exponential term, to get over that barrier, and that's called quantum tunneling. So there's still some, you're telling me there's a chance? Yes, there's a chance that I'm going to overcome that barrier, and the fusion happens first to deuterium, where it converts to a neutron, and then on to get eventually helium. So there's a crude analogy here with the way that that Giovanni discovered that Bitcoin's price goes with Metcalfe's law. It goes as the square of the adoption. So we can think about, instead of the density, we can think about the adoption squared. And then the question I want to ask is, okay, well, what about supply term? Does that matter? And that turns out you can model as an exponential, really 1 minus an exponential. And it's a pretty good fit for the halving schedule. So that's what I've done for these regressions. And the term looks like 21 million times 1 minus an exponential with a characteristic time scale in the exponential term of 5.77 years. Now, strictly that's in block years, not calendar years. But in recent years, the difference has been relatively small, within a couple of weeks. In the very early history, it was different. So now we're at 17 block years as opposed to 16.3 calendar years. But the reason that for that 5.77 is that that's 4 divided by log 2. And the way that works out is that gives you the halvings on the 4-year schedule. And as people who know about the supply algorithm, they'll know that, the first 10.5 million was issued in the first 4 years, and it was just linear. If you expand that exponential, you get basically to first order, you reproduce that same thing, because you get 1 minus a linear term, and that's what you get. So the chart shows the black line, the actual supply, and it's a log linear chart. So it shows how the log of the supply grew. and then asymptotes towards 21 million, which is the red dash line. And then the blue is this exponential approximation that fits quite well and that actually crosses at the 4-year because of the way that, it's calibrated to that. So that's the form that I used in the regressions that I'm going to show you. Very early on, it would look like price is adoption squared divided by time, because you just, for the first 4 years on this linear relationship, and then it would become slower and slower with time. Okay, so I also want to look at liquidity. So what I'm setting up here is multilinear regressions that have, more terms than we're used to. So in the white box, we've got the usual log of price equal to some constant plus another constant times the log of age. And we use log 10 throughout these. So we're adding 2 terms. One is got this second constant parameter B2 times M3, and that's the liquidity term. And actually, I've looked at both the M3 index and the percentage growth of M3 for that term. We do not need to take the log of this, because if we're looking at percentage changes, then we're already effectively looking at something that approximates a log.
Yeah.
And then the final term is this supply term, and we've taken the 21 million into this coefficient B3, and then we've got log 10, and it should be a log term because you want it to, it's basically kind of in a ratio with the price, right? There's a consideration there. So we've got the usual terms plus a liquidity term, either M3 index or M3 year-over-year growth. And for people who were on last week, I went through a lot of that, and we were looking for correlations and Granger causality and so forth. Okay, anything else to say on that slide? I think that's it. Oh, okay, so we do 3 regressions in each set. We do an ordinary least squares, then we do a quantile regression with all of the data. So we're looking at the median level, the 0.5 level that provides us the equation and the fit. And then we look at the core. And the way you get the core is you take that quantum regression median level for everything, and then we just we filter out all the residuals above the line and only keep those below the median. And then we use the data points corresponding to those residuals, and we do a second quantitative regression for its own median, but again for the lower half. Okay, so I did 18 different regressions. I looked at 6 sets. So for each set, we've got this base of the ordinary least squares, the quantile regression, and the quantile regression for just the core. In order to get a baseline, I did just the age first, and we see the usual results, where the slope for the OLS is 5.7, for the quantile regression for all, it's 5.8, and for just the core, as we know, it's a little bit higher, it's 5.9. And the errors on the slope we see are very, very small, and the R squared is high, especially for the OLS and for the quantile core, and we've got a high F-test number. The regressions only supply the F-test for the ordinary least squares. Then we have these additional 5 sets of these, where first we add a supply term, then we add a supply plus a liquidity term that's M3, which is the index, the OECD index, which I actually reconstructed and set to 100 when Bitcoin starts, using the growth rates. And then we've got another one that fixes the supply term to be an inverse power law of 1 instead of making it free floating, because really, if it's going to do anything, it's going to be proportional to the supply, you would think. And then the same thing, but with the growth rate, the M3. And then finally, just dropping the supply term and only looking at the growth rate, the percentage growth rate year over year. That's what the delta M3 corresponds to. So this is a table that summarizes all the results, and we'll look at these in detail set by set. Okay, so just including the supply term, what we find is, and allowing it to be free floating, so it can pick a weight that optimizes the least squares or the quantile regression in the median. What we find is that it causes the slope to decrease, but only for the first two, not for the core relationship. And the errors for the age regression do go up, and the supply weights are negative as you would expect, but they're more than -1. They're more than just inverse to the supply. In other words, if you just double the supply, you expect the price to drop in half, right? And that would be a -1 regression since we're using a log term. But if you look at the core, the supply weight is -0.005. It's only 0.5%. So it had no effect at all. And it gave us a very high R squared of 0.94, very close to the OLS number. So the three regressions are shown in the log-log graph. And you see what happens is trying to include a supply term causes the OLS and the QR all to kind of bend down, right? And they're actually trying to approach the quantile regression for the core that only uses the below median, and that's the red dotted and dashed line curve that you can see fits the core power law quite well. So the takeaway is that the supply does seem to affect the early volatility in bubbles, or to be reflected in the early volatility in bubbles, but not the quiet baseline price trajectory. And ChatGPT says this actually supports your core quantile regression below median as being the more stable structural trend model for Bitcoin. So one of my takeaways from this is maybe why people got very caught up in the stock to flow model early on, because they were paying attention to what happens in the bubbles, where things get quite exponential and also quite emotional, and that draws in more people, more observers, and people tend to observe the highs more than they observe the lows, right?
Right.
And so, the stock to flow worked for a couple of cycles. In other words, it was, shall we say, potentially useful. Now we know it's useless because it's failed by an order of magnitude by now. Okay, now this one I add to the supply term, again, free floating. I add an M3 weight term, and this is the index, not the change in the index, but the absolute value of the index. And you get kind of nutty results for the OLS and the QR all, where you're overfitting. You get a very small slope for the age, but also a very large error on the age term. And then you get a supply weight, which is extremely high, inordinately large, -5, -6. It's putting all the weight into the supply, but it's also putting a very high weight into M3. The F test is very much degraded from what we saw before. The errors on slope are very high for all three. But when you look at the QR core, again, the supply weight drops to close to 0. It's 0.06. And the M3 weight, it drops to close to 0. It's -0.04. It's actually slightly negatively correlated with the M3. And it gives a decent R squared. So it pushes the supply and M3 weights down by huge amounts, by factors of 100. And then it puts you back to a slope with the age of 5.96, very close to the age to the 6 relationship that we expect from Metcalfe's law and from the adoption. Okay, so then I said, well, it's kind of crazy, a supply weight of -5. That makes no sense. So let's just fix that to be a supply weight of -1, but allow the weight to vary for the M3 for the liquidity. And here's what we get. We get M3 weights of -1.2, but in the core -0.7. So here we have a slope for the age, which is actually higher than one would typically see with a relatively small error and an M3 weight, which was actually uncorrelated negative. So why would that be? Why would the liquidity be negatively correlated? Well, because it's actually appearing to be negatively correlated with Bitcoin's fair value base trend that we see in the core, in the red line. So strong dependence on age and the suggestion that in low liquidity environments, Bitcoin tracks the structural organic growth, which is driven by adoption, not by liquidity.
Yeah.
And when you see that people are allocating into Bitcoin as a store of value or a hedge, not as a momentum trade. So liquidity is associated more with momentum and with bubbles. When liquidity is abundant and other markets are saturated, speculative capital spills into Bitcoin, pushing price well above the core, triggering bubbles.
Yeah.
And now we're seeing that starting to happen right now with the increase in price from last week of $10,000, right, of Bitcoin, because the liquidity from Q1 is starting to kick in.
Yeah, I like this. I like this interpretation. Yeah.
Okay, then instead of looking at the M3 index, we look at the M3 growth, because we showed last week that it's that one that's more directly tied to triggering the bubbles. And the one thing that we got Granger causality for, or very close to it, was when we had the 1 year growth in M3 reach 7%. That seems to kick off in the transition zone. It doesn't carry, liquidity doesn't carry you through the whole bubble. You need momentum and FOMO and players coming in, but it can trigger the bubble.
Yeah.
So here what we see is we get slopes that come down some to 6.2, 6.5, very small errors in the age regression. We've still got some supply waiting in here, so keep that in mind. But the M3 delta, the growth in M3 weights are pretty small. They're 0.01, 0.02, and we get good R-squared results. And the F-test gets back above 10,000, not as high as the original, but decent. So these results support the idea of gradually absorbing global liquidity with bursts triggered by macro surpluses. When you get liquidity shocks, then you can trigger a bubble. The other thing that you notice in here is you see these big post-COVID bubbles when you had the huge liquidity spikes in response to COVID. And they're very clear here.
Yeah.
And you see kind of a quantum jump, and then it falls away again.
Oh, so cool.
And then we get back to the QR fit, below the median.
And this could explain why we had a double peak. In that cycle, right? We had like an early peak and then a second one. Yeah, it's very interesting.
You look in that smaller log linear chart, it's even more apparent, right?
Yeah, it is.
This bump up, and then it's right leading into the double bubble, and it has a duration that's sort of similar to the double bubble.
Yeah. And what is happening right now? Because I see like it's bending up or something.
Let's go to the next one, because that shows what's happening right now, I think, more clearly.
Okay.
Because with the next one, we take the supply weight out, because we've sort of already learned that supply doesn't matter.
Yeah. Also because right now basically it's fixed, right?
Certainly by now it's fixed anyway, So if it mattered psychologically before, it doesn't now, because it's only 0.8%.
Yeah.
And the capital flows are much, much larger than the new minted supply.
Yes.
So this one has no supply weight, but it does allow for liquidity weight with the growth, the delta M3. And so we still see that effect of the post-COVID liquidity, but it's a kind of a smoother behavior.
And sorry to interrupt you. How did you adjust the weight? Did you just use a function that
it's just a regression here. It shows the regression equation.
Yeah.
So it's just a multiple linear regression. So M3 growth is free floating.
But how did you make it as a function of time? So your
I have
weights are
the M3 growth over the entire history. So it's the year-over-year growth of the M3
okay.
over the entire price history shown here.
Yeah, I will probably ask you some question because I was trying to do something similar. Because when I do my model, my price model based on liquidity, I notice that there are changes in scaling, right? So if you change with scaling, sometimes you get a very nice match, but then it doesn't match somewhere else. So I was trying to do something like that, where I think it's very similar to your idea of weights. But I want to learn from you how to.
No. Here's my suggestion.
Yeah,
I think you're using the absolute value of M2 liquidity globally, right?
yeah.
Yeah, I suggest that you use the incremental change, the percentage change.
The percentage. Okay.
Year over year, you maybe try quarter over quarter, but use a percentile change for that.
Okay.
That's what I'm doing here. And then, find what weight the regression gives you.
Sounds good. Yeah.
Yeah. This gives us a good R squared 0.94 or 0.95 in the OLS, 0.94 in the core with only this liquidity delta term. And its coefficient is not that large. It's, 0.01 basically for the QR core, a little higher for the other two regressions. But you still see that liquidity bump, and you still see, a little bit of turn upward in the red dash line. I don't know why it's not drawing all the way to 2025 in the lower plot. It is in the upper plot.
Mm-hmm.
So you see a little bit of a bend upward, perhaps. It's hard to tell. You'd have to kind of blow that up to see. The overall conclusion is that when Bitcoin is below median valuations, the power law of age still dominates, liquidity helps, but its marginal effect is weaker. But where it has still some influence is when you're basically kicking off the bubbles is when it has the most influence.
Mm-hmm. Maybe that bending up has to do with the ETFs.
Yes, that absolutely is the ETFs in the early 2024.
Mm-hmm.
Yeah. Okay. So conclusions. The weightings for supply in M3 can be significant for all data. And that's only really because of the bubbles. Supply is clearly of minimal relevance now, and the bubbles can fool you into weighting supply. And that's why perhaps the stock to flow model appeared plausible for the first 8 years or so. It's all models are wrong, and it's now entirely useless. In the Power Law core, the quantile regression of all with residuals less than 0, and then redo a second quantile regression on just those, the weights on supply and M3 fall nearly to 0, and that's true whether you use M3 or M3 growth. The Bitcoin has a Power Law core plus faster than exponential bubbles up and down that are superimposed but return to trend. And as we showed last week, or in the last show, the liquidity growth year over year is greater than 7%, can trigger almost a year later, but not sustain the bubbles. So that was what the prior show was 2 weeks ago, I guess.
Yeah.
And just as a bonus, I wanted to show the projection with that regression that also includes the delta M3, the growth in liquidity, and making an assumption that we do get a liquidity bump up to 10% this year, and then it falls back to its mean trend, which is something like 7%. And if you make that assumption of a bump this year, which I think we have a good chance of, then this is how those three trend out over the next 5 years. In the core, which currently is in the mid 60s, I would say for the quantile regression core price, it would be 84,000, at the beginning of next year, and would rise up to 283,000 by 2030 for the core. but the mean for all the prices, would be 120,000 at the beginning of next year and rise up to the 400,000 neighborhood in beginning of 2030. The other thing to notice is that the difference between quantile regression all prices and the core does gradually come down, so that it's about a third less, because volatility is coming down in the bubbles, and this is reflected in the way these trends behave.
Very cool. Now, for what concern the growth of M2, right? Are you using an exponential model for the growth of M2?
I'm using historical
M3.
data for M3.
M3, okay. So is it
But
growing
But this one assumes, yes, this is a exponential 7% going forward. So it has a bump up to 10%, and then it trends back to 7%.
Mm-hmm. Because this is one thing that I was thinking in the last few days. We see this strong correlation between the price and global liquidity, but we know that Bitcoin follows a long-term power law, right? While
Right.
M2 and M3, they should follow exponential. So if you're trying to project long-term, how these two things combine together.
Right. Maybe there isn't causality. I mean, I showed that there's only causality in the transition zone 2 weeks ago.
Okay.
Maybe there's no causality. Maybe what happens is that Bitcoin is given us 10 times as much as 7%.
Right.
Right. Maybe that's all that's going on there.
Yeah. It's just kind of almost an illusion that there is this very strong correlation. It's just temporary, but it's more about burst, right? That happened during the bubbles. Yeah.
I have two conclusions. So I'm going to publicly state that Michael Howell is not correct.
Yes. I was suspicious of that from the beginning,
But I showed it myself. That relationship is there, but what is the causal nature of that relationship? Now, he claims Granger causality. I did not find Granger causality.
Right.
I found that you got close to Granger but I had a much longer data set than he did.
Yeah.
So I want to challenge him on that. And then secondly, I did not find Granger causality in the bubbles. I did not find Granger causality in the core. I only found Granger causality in the transition zone.
Yeah, this is so cool that we are actually have this tri-mode view of Bitcoin, right? It's so important because it gives you insight that you will not get if you just thought about Bitcoin as one single process. But there are different processes, and the transition zone are not well studied, but it's very interesting that you find this correlation with M3. Very good.
I want to say that our audience, being exposed to this is 1 in a million, because 1% of people really get Bitcoin. Within that, maybe 1% really get the power law. And then within that, maybe 1% get this bimodal and trimodal nature of the way it develops. You combine those three, it's 1 in a million, guys.
Yeah, very secret knowledge, talking about.
It's public. Thanks for watching.
Very good. And so let's look at this bimodal behavior right now. I'm going to share some of my screen. Okay, so this is the trading view indicator that actually I developed based on this concept. I need to add, talking about that, I'm going to actually work on modifying, because I'm actually using the Markov process like you did. But I just did it 2 modes. I'm going to add a third mode. You can see there is like you can see it with the transitions, and you can see that it's a very fast transition, but I should color code it too. I should ask the Markov process to give me yellow, something like that, and mark these regions, because they are very interesting. But this is where we are right now. It's nice by way that we had this recovering in price. Um, we are not yet above the power law that it's kind of, it's not the thing that we use to actually find the regions, but it seems strongly correlated with being above or below the power law. It's not quite, but kind of. And this power law, as a reminder, it's basically kind of a compromise between the bubble behavior and what we call the core power law. I really love that term that Stephen came up with. But we are moving again. Let me refresh the graph because it's showing to kind of a little bit. Yeah, the number was a little bit out of focus. So, we are this is where we are, and we are supposed, if we want to go back to above the power law, that right now, that value, it's close to 1 or 2, something like that. That is what the power law says is the reference value. It is really interesting, right? Because you can see people will always say, "Oh, we will see," right? When we talk about the power law, we will see if a power law holds. Or they say, "Oh, you retrofitted." Well, I started to talk about the power law in time since 2006. I used actually to have like a little band here to show since when the power law actually was. I started to talk about power laws in Bitcoin much earlier than that, 2012. But the one in time happened here. So all these, since starting from here, all the way here is actually, forward predictions, that happen after the discovery of the power law. So, and you can see it's holding very well. But, since we started to get a little bit more attention and being a little bit more public, so let's say about 1 year ago, kind of February, right, when I had that interview with Andre Jik. Well, this is what Bitcoin has done. It is basically oscillating around the power law, right? So I don't know why people still doubt it or have problem with it. It's clear that Bitcoin is, in fact, actually I do have a graph. I just made another indicator that calculates the R square live, and R square is growing. If you calculated R square as a function of time, it's actually going up. So anyway, so the main question right now that many people may have is, are we going back to to this kind of behavior where we see two clear modes, and usually we have this we call this red mode where basically Stephen calls it the turbulence mode of Bitcoin, and again I love it as a term. We are not there yet, but it seems that we are going back, right? So many people dismiss the cycles, mostly because we spend that, we corrected, we spend it a lot of time below the power law. Usually that doesn't happen in that way. Once we go above the power law, we stay above the power law for about 2 years. It happened only once where kind of here, you see, where we went below the power law, the trend power law, but it really lasted a very short amount of time. And now, because there was something weird about the liquidity, we were missing liquidity to support or at least maybe kick-started, but I think it was a combination of things, right? Maybe the election, Trump was already talking about tariffs, so maybe there was an anticipation and fears and uncertainty associated with that. It was a bunch of enthusiasm in the beginning, and then people started to get worried. I think when I say people, it could be big players like institutions and things like that. But something else is happening right now where I think it's a mix between been used to this tariff regime, right, the situation, and kind of including it in the evaluations. And it's something that the market, because the biggest thing about market is uncertainty, right? So it's bad news can be eventually digested and priced in. So they are starting to price in with tariffs, right? And the market is covered. Plus, we will need more time, but it seems that finally Bitcoin is showing signs of being not correlated with the market. That is actually something interesting to explore maybe for future episodes, right? Do we see signs of Bitcoin doing its own thing, or maybe even becoming a safety event, for situations like this, like gold is? So, maybe there is some signs of that. But, we still have time. The 200K that independently, I use different methods and I come up with a value of 200K, and Stephen used others. And I like when he makes these calculations, and we always kind of converge to this number, right? Right, Stephen? You also come up with a number
similar, yes,
close to 200K.
Mm-hmm.
And this is predicated on things behaving like in the past, right? We don't know yet, but so many people dismiss the cycles, like, okay, cycles are over. I think it's too early to say that, but it's also too early to say we are back to business as usual, that we are actually going to have a normal cycles and we are going to reach 200K. We don't know. We will have to see. We will have to monitor. But this is a nice development that we are going up. And this was kind of, there is this idea that I have mixed feelings, because also what I'm going to share some other graph of what Stephen is showing, but I have this other trading view indicator that I'm going to share with you in a second, that shows a relationship between. So basically, I made a model, but I'm going to follow the advice of Stephen and using actually changes in M2 and 3. Here I'm using the absolute value. So I made a model. Many people just show M2 superimposed on the price. So the price here is these bars that you see here. And then what I did, I used this supposed power law. I think it's not like one of these fundamental causative power laws. It's more like kind of a relationship there that seems to hold. It's kind of an empirical relationship that is probably an approximation of a real process, a real relationship. So there is a strong relationship in general between liquidity and Bitcoin, but it's very complicated. It's non-linear. It's not like a simple one, and probably it's more like it's not really causative. It's like they are moving along. Certain, the liquidity goes up, Bitcoin goes up. Now the main question is, can you see some agreement between features, right? That if you do it just by eye, our eye tends to see patterns, right? Like basically Jesus on a tortilla, right? So, oh yeah, okay, this section here seems to kind of follow this one. This section, we are going up. Okay, liquidity also goes up, right? So these are model you see here is basically using this long-term trend over 10 years, where it does look like a power law between the two quantities. And if you use that relationship, you have some kind of power law, power 9.3, then you get these models, these price models. You can say, okay, given this relationship, what is supposed to be the price? Is the problem? I think it should not be taken at face value, because you can see this is what the scaling problem, this scaling problem that I was mentioning to Stephen. You can try to match features like these by using the right scaling, and it looks a very good match. And then you don't get a good match here, for example, right? Even if you can still say, oh, okay, there is some features like this, the price is going down here, and it's going up here, so here evidently it's clear there is like a bottom, corresponds to this bottom, but the peak here is over there, while the peak is for the, you can use this peak or this peak, right? So if you're thinking feature by feature, the correspondence is much weaker. And what I tried to do here, I created this indicator that looks basically, first I smoothed the 2 time series to reduce noise, and then I calculated what is the winning rate. So many times we go up relatively to when we go down. But it's an interesting thing per Bitcoin per se, right? You are actually, it's a picture that we also got when we calculated the returns, right? The average returns. Here I'm averaging over 1 year, and it's basically the winning rate, right? So it's kind of interesting to notice that when we reach bottoms, the winning rate over 1 year is about 20%, which is interesting. And it's very consistent. That is another way of talking about that support line. That support line seems to be very, very consistent above all the history of Bitcoin. This is why we have a flat support, flat value for all these bottoms. And these are the peaks, right? And you can see the bottoms are much more correlated with liquidity, while the peaks are not, right? Because we see an early peak in price, and then liquidity seems to peak later. And now, we see this turning around. This is something that a lot of people are debating and discussing, because we see an explosion in liquidity, and the question is price going to follow? Right now, it seems that this recent rally seems to correspond to this kind of a knee here. But yeah, what is your opinion on this? How reliable are these feature matching between global liquidity and price?
Yeah. Well, I want to see 7% year-over-year growth. That's what I want to see. And that's my trigger, And the problem is that the available OECD M3 data, the last available data point is October. But M2 is starting to pick up for the US and globally. And I saw some other liquidity numbers yesterday, and they look like they were running at like 2% per quarter. So that would be sufficient.
Yes. So yeah, exactly. Because in particular, if this power law, even if it is just temporary, holds, right? Because if you have a power of 9, I think I did a calculation. Maybe you can verify, like just a change of 10% in liquidity corresponds to a change of 2 in price, if that relationship holds, right?
Roughly. I mean, basically, you can just say 1% liquidity gives you 9% or 10%.
9%, 10%.
Yeah.
It's incredible. Yeah. So, hopefully this is correct, at least temporarily, that Bitcoin is responding to this liquidity increase. I will not take at face value this model because of this scaling problem, but we are going in the right direction, it seems that we are going in the right direction. Anyway, last thing I want to share, I did an update of the quantile model. We have a particular way of doing the quantile model. I'm going to share that with you in a second. Okay, here it is. here. Okay, so the way we do it, because you can do it in different way, right? The quantile regression is something that we have discussed before and went through, in terms of, let me find the right slide here. Let's start from this. What is the best way to do the quantile? But basically, the main idea to explain to our followers is that you take the data and then you sort the data in terms of quantiles, right? So basically, you're saying, here are all the data points. I'm going to put them in order of value, like, for example, price. And then I'm going to take only the first, right from the bottom to about 10% of this distribution of values, right? And then I'm going to fit this value only, and that will give me the 10% quantile. Then I go to the 20% quantile. So basically, I'm getting 20% of the data point sorted from the lowest value to the highest value. And it's an interesting way of doing it. You're getting, the problem is, as we discuss it in this episode and any other episodes, that Bitcoin has this bimodal nature, right? So there is a core power law behavior, and then there are the bubbles that behave in a very different way. We have some kind of a log normal distribution with long tails, etc. And what we see over time, that the bubble decay. They became smaller and smaller with time. So if you did a simple-minded quantile regression, when you go to the higher level, you're basically trying to fit power laws through an exponential decay. Or really, it's a exponential decay on top of a power law, right? So because the way of doing this quantile method, right, you are feeding to the algorithm, not directly, not linearly, the prices and the time. You're feeding the log of the price and the log of the time. And then you're asking, okay, find me a linear regression through this data. So if you're doing a linear regression through log of price and log of time, you're going to get power laws. And the algorithm doesn't know what data is dealing with. It's going to find the best power law it can find. And if you have something on the top will look like an exponential, it's getting confused. It's going to try to fit whatever it can, right? It's trying to do its best job. But it's a very misleading graph because you cannot really fit a power law through an exponential. It's going to give you misleading result. In fact, one of the things you notice when you do that particular type of quantile model is that the curve, we have these parallel lines at the core, because basically the quantile model is just another way of doing power law fitting, and it works perfectly. Is indistinguishable from a least square regression, very similar to the least square regression, that is a more traditional way, a simpler way of doing regression. And it's, basically you're getting the same result up to about 40 percentile, right, Stephen? Something like that.
Yes.
That is where the core is, right?
Yeah.
And when you go above, you start to see all these straight lines that are at an angle relatively to the core. That is a nonsense answer from doing the quantile model, because when these lines actually are going to cross each other, and it's a non-physical result, right? It's a mathematically correct result, but in physics we have a lot of things like that, where you do the calculation, you get a mathematical correct result, but it means nothing physically, because you introduce some assumptions that were not correct, like negative mass or something like that. So a better way of doing the quantile model that we discussed, but giving you an update, so a kind of revisit the entire idea, is to use the quantile model up to a certain deviation, let's say up to 40% quantile, and then look at that will be your reference level, and then look at the residual. So right, so you're taking the residual means the difference between the price and this quantile model that you created, where you're using the median or you're using the core, right? And what you see, if you're doing a plot. This is what is called a log linear plot. So I'm taking the log of the deviations versus the linear time. And you can see there is these bubbles, right? This is what you're seeing here are basically the bubbles that are the major components of the deviations. They look like they're going down in time. They are decaying. And so one way of fitting that makes sense here will be a linear fit of this log linear graph, and a linear fit of a log linear graph gives you the straight lines now are not power laws, are exponential. Now, using the correct mathematical shape for this particular process that you're observing, and it's not kind of a coincidence, or it's not. I think it's something fundamental about the behavior of Bitcoins, but because you will expect over time, basically this is a measure of volatility, with this volatility to decrease in time. So there are two things that are fundamental in Bitcoin behavior: is this long-term power law trajectory plus a decrease over time of the volatility. So it's a pretty good model, and it has the advantage that it is not focused on some kind of cyclic nature of the bubble. So there is no, in theory, you could even add that, right? And you could even fit. In fact, I did a quantile model with cycles. I will discuss it another time. But if you wanted to avoid to be stuck to a particular length of the cycles, you will have at least one more component, that is this decay. When you put it together, so you can go back, right? If you do this quantile fitting using basically straight line in a log linear chart, and then you go back and kind of glue it together with your core model by reconstructing, right? Because you know that these are deviations, so you can calculate what the price should be given this deviation, this model of a deviation with are the straight line. So the straight line now are a substitute for this decay that you're observing. It's a simplification of this decay that you're observing in the bubbles. Now, this is weird because we are supposed to see, this latest data is weird, right? Because it doesn't follow what we are observing before. We don't have yet all the data up to the peak, right? But it's some new information. So
that proves your point, though, because if you can go back for a second, it proves your point, because if you look at the purple line, which is the 0.75, it's got the 0.75 going through the fake out that we experienced in early 2024,
right?
Because we don't have our true bubble yet. Because the quantile just forces a fit.
Exactly.
Essentially. So it's demonstrating the point that you were making.
Yeah.
About at the higher levels, the quantile is less robust.
It's less robust, And so you're doing your best, and this is for sure is a better way of fitting this behavior in the residual than trying to fit power laws, right? Because there are no power law. I don't see any power law through this thing. It's ridiculous. It's close to be an exponential than a power law. And when you do that, then you get this interesting shape where you have a core, right? I try to differentiate. You see the dots. The dots represent the core. But it's indistinguishable from the normal power law that we always discuss. And it's consistent, right? You go to the 10% quantile, 20%, basically almost more than 50% of the data, actually, right? Did we calculate that is about 52% or something like that? 52% of the data actually fall within this core behavior. And then if you want to try to model the behavior of the bubbles, I think this does a good job. And it shows basically that over time, you see how now the lines, the upper line, do not ever cross the core. They kind of, it's almost like an asymptote, right? Because this is the behavior that you're going to expect. they are going to come closer and closer to the core, but never crossing it. That the other, we can call it vanilla quantile model. It's one of the problems with that model. But eventually, if you don't do it correctly, eventually they will cross the core. And this is how it looks like in the log linear chart, right? It has almost like a beak, like some kind of bird or something. It's interesting. But yeah, this is an update of the model that seems to hold. It's now, I don't know if we are going back to these upper quantiles, but again, now it's consistent with this 200K, because the other one, another problem with the other model, if you take it at face value, it gives you much higher. It tends to overestimate the peak. You did something similar, right, Stephen? It gives you a much high value for the peak, but I think it's unrealistic.
Probabilities of hitting levels. By the way, for people that are looking at this and wondering where the $1 million price point is, it's just below 14, because this is log price in natural log.
Yeah.
So 14 is a little bit above $1 million.
Yes. And this is the linear chart, right? So I didn't go all the way to 1 million because you will not have seen it. But basically, this is what we are observing. I don't know why it didn't project the core. It should also project the core. But yeah, so this is what we are seeing if you're doing the log graph. It looks basically, when people talk about Bitcoin not growing fast enough, I don't know what they are talking about. We are seeing these super parabolic graphs, right? Because we are talking about the power of 6 and the parabola. And when people say, "Oh, the price went parabolic," they don't use it correctly. Usually they mean exponential, but parabolic is also pretty fast, right? You are squaring, but this is a super parabola, right? It's almost undistinguishable from an exponential. But we make a big deal about not being not exponential because over the long term there will be a difference, but also because we have so different characteristics. So it's a fast process. It's not diminishing returns. There are diminishing returns, but it's still a very fast process. Anyway, let's take a couple of questions if there are questions. So maybe this one. What is the current price floor? Do you have a value in your head? I can double check it.
Well, if you just take the core and run the quantile regression through the core, it's around 64,000, some number like that. But you could go below that because, that's just the middle of half of the data.
Right.
Right now, I think that the standard deviation is around 0.2 in the log, which is a factor of 1.7. And I think the fair price on a quantile regression median for all the data is in the mid 80s. So that would, and if you only drop one standard deviation, which is really what we've observed on the downside, that's something like $50,000.
50,000. And the support, that is that line that we seem never to cross, is about 40,000. That is about 60% from the reference value. So yeah, that is. But yeah, I don't think we are going to revisit that low value because there are no signs we are in a bear market. It's more like Bitcoin wants to go back to be bullish. But we will see. Anyway, I think this was one of the few questions that were available to us. Okay. Then if there are no other questions, we can close here. Maybe there is a. Okay, I think I misspoken. Let's look at this one. Maybe you can answer this one.
Again, I would say that it is the change in liquidity that we look for. And, I'm not quite sure whether it's the year-over-year change or the quarterly change. We had liquidity was low in Q4. It picked up a lot in Q1. Typically, people are saying there's about a 3-month lag. Howell will say about 11 weeks. Others will say 13. It's in that range of about 1 quarter. So if that's the case, you expect, Bitcoin to be stronger now. What I found was that it was the growth in liquidity. It had to get above a threshold, and that threshold is 7%. And I think we may be roughly there now, but I don't have it for that particular data series that I use to demonstrate that, because that has a lag in it when they collect it and report it. So I think we are in the transition region now. We're seeing liquidity pick up. If it's above 7%, that should be enough to kick us into the bubble region.
Yeah. And Stephen is correct, right? So people give a lot of attention to these features, so structural feature, I call them. I think it's probably processes that are happening to both assets, and they are getting affected by similar processes, and they kind of look the same similarly. I think the bottom, probably there is something about the bottom where they seem to align pretty well with maybe some delay. But yeah, the fact that we had a turnaround in liquidity, that is more significant than, we are following 1-to-1 what liquidity is doing. So it's more about structures, like changes. This is why I made this model looking at direction. So it's more of a direction, the general direction of one time series versus the other. And in general, it's positive because, the money needs to come from somewhere to go to Bitcoin and to make it go up, right? And so liquidity, it's a sign that there is money where people, the institution and whatever feel confident about moving money around, and in situation like this, it finds Bitcoin because I think people start to think about Bitcoin as a heaven for their assets. It is a good development. But and maybe we can study this next time. How strongly correlated Bitcoin is to gold or traditional markets and things like that. That may be something interesting to explore. Okay. All right. Then we can conclude here, and we will see you. Oh, maybe we have another question. Can you answer if heavy sell off from early adopters impair with Power Law? This is something that we can show next time. There have been studies. Actually, another physicist called Sornet, he did. But this is another thing we can do because we always present original content. But maybe, Stephen, we can actually review interesting papers, right? That could be another thing we could do on the show. And there is this very interesting paper by Sornet that maybe I can review next time, where he talks exactly about these kind of things, the behavior of long-term, older, and short-term holders. And he has even some very interesting result where he shows that holding time of investors, Bitcoiners, follows a power law. So even the holding time is a power law. So we can discuss that paper next time. And there is a beautiful chart. And so I'll give you a preview, but I'm going to show it next time, where it shows that short-term holder and all-term holder, and all, you can come up with an arbitrary definition of what all-term holder is. But in the paper, they say anybody that didn't spend more than 25% of it, didn't sell more than 25% of their Bitcoin over a 4-year period. That's what qualifies you as a long-term holder. And what you see is that the long-term holders sell regularly at the top. And then they tend to buy at the bottom. In fact, probably they are the one triggering the top, the collapse of the top, while the short-term holders do exactly the opposite. They tend to buy at the top because maybe they joined recently and they get excited about the bull run, like Stephen was saying. It's what attracts the attention of newcomer, and then they get scared and they see that there is a collapse and they want to sell, because they think that we are never going to recover, and they tend to sell close to the bottom. So it's something that you should not do. You should try to avoid. But yeah, it's an interesting. And so, yes, I think there was recently, was not really the top, but we had a local top, right? When we had it 108, there were many long-term sellers, maybe because psychologically 100K was a particular goal. Maybe they told themselves, hey, when we reach 100K, we should sell a chunk of our positions, But yeah, there was a lot of long-term. The data shows that there was a lot of long-term holders that sold at that time. But no, they don't. To answer your question, the power law is not impaired. What the only, if anything, the fact that we didn't have a bubble, or at least we didn't have a bubble yet, makes the power law stronger. Because remember, the bubbles are when we deviate from the power law. And the only reason we have fall of a power law is because there is a component of a bubble that goes up, then one that goes down, that basically kind of cancel out the going up. But when we go up, so that is what one of the things that I always say when somebody says, oh, is there something that can break the power law? I say, yeah, the power law has been temporarily broken 4 times. Every time we had these bubbles, we temporarily broken the power law, at least in the branch when we go up. The behavior became exponential. We leave a power law. But over the long term, if you average it out, because we have a component that goes up and one component that goes up, they basically are canceling each other. And then the power law is restored. But if you don't have that, then you have even stronger power law than before. So the power law is not impaired. The only thing was, we were expecting one of these bubbles, because I am okay with temporarily leaving the power law because it's exciting. There are opportunities for maybe trading or doing futures or options, whatever, if you are in that kind of things. But the power law is stronger than ever. I don't know if you want to add anything to that.
No, smart money reinforces the power law, basically, is boiling it down. Yeah. And power laws are more stable than exponentials. So the smart money has recognized the nature of this.
In fact, today I even made a post saying, one of the things that you can always answer to people when they say Bitcoin is a Ponzi scheme, tell them that Ponzi schemes don't follow power laws. They usually follow exponentials. So that is another very strong application of a power law to show people that, it's evidently not a Ponzi scheme. Otherwise, it will have grown as an exponential, not a power law. Power law is something when you have something systematic, organic, that has fundamentals, and it's not artificial, it's not speculation. So, but that is another thing that we could explore one day. What is the true meaning of a power law, right? In terms of growth, etc. Why it's stable and all kind of things like that. There are a lot of topics to explore. And there is this question that, again, it's also a kind of worm, the difference between finite and scarce. So, we could dedicate an entire episode, maybe even more, about differentiating. In physics, we have this very interesting concept that eventually I do want to explore, that when you create things in physics, right, there is symmetry and conservations. So, for example, when you create from energy, you create particles, you tend to have plus and minus, right? So it's a finite amount. In fact, the total energy of a universe also, it's actually zero. Imagine that, right? We can create the entire universe from zero energy. And the reason is because you can redistribute this finite amount, in fact, even zero, and then get everything out of it, right? This is what Bitcoin is. It's a ledger. You're simply redistributing things around. And that is this very fundamental property that is constant, that is finite. Uh, and that is very physics-like concept. And I don't think it has anything to do with scarcity. It has to do with the fact that it is not inflationary. That is, I think it's what people mean, but that it's not just a semantic thing. It's really a fundamental concept that maybe, later on we can explore. But yes, what do you want to say something on this, Stephen?
Well, it's completely scalable because it has 15 digits of decimal precision.
Yeah.
It is the first ever fully scientific standard for money and monetary technology, rooted in energy, rooted in cryptographic math, and it's more real than any other kind of money around.
Cash or gold, yeah.
Gold, gold is real. Bitcoin is more finite than gold.
Yeah.
We all know about that, that meteorite, that asteroid. Which one is that? I forget which one that is.
Yeah, I don't remember, but yeah.
It supposedly might have so much gold. In any case, the scarcity can be continuously redefined. If you start thinking in sats, right? There's 2.1 quadrillion. So how scarce is it is a function of the price. Yeah. It's very scarce at $50,000 today.
Yeah, no. maybe sometime we can discuss that. But in particular, I want to make it. I want to use this analogy that we have in physics, of conservation laws. To me, it's more conservation of money law than anything else.
Mm-hmm.
And there is a one-to-one analogy with this concept. In fact, even so, conservation laws are linked to symmetries, and it's a very interesting topic that we could explore. But anyway, thank you so much, guys, for listening to us, and we will see each other next week. Bye, everybody.